Hello everyone, welcome to the Things Network Conference. I'm Ehsan, an application engineer at Nowi, and today I'm going to talk about designing an autonomous LoRa node using energy harvesting technology. Before going into details, let's have a very brief introduction about what Nowi is and what it's working on. Nowi is a semiconductor company located in Delft, the Netherlands, which works on energy harvesting PMICs with the smallest assembly footprint. We're talking about the design of an autonomous LoRa node. Let's see very shortly what an energy harvesting system is. An energy harvesting system is embedded in an environment which has energy, and that system can capture and absorb that energy from the environment to run and work. The first block of an energy harvesting system is the harvester. Harvester captures that energy from the environment. And then it needs to be stored somewhere. But the problem is that the voltage is not enough to be stored in a storage. So there is a block called PMIC or EHPMIC, which does this job. It boosts the voltage from the harvester and it puts and stores this energy into a storage. A storage can be any type of battery, or it can be a supercap or just normal capacitor. And then this stored energy can be used later for different purposes. And then this energy goes to a load. This load can be like an MCU or any type of transmitter like a LoRa transmitter, or it can go to supply a sensor. So these are the four building blocks of an autonomous system or autonomous sensor. Since we are talking about energy harvesting, we need to think about the other side, which is the consumption. The consumption of these systems comes from two sources, and this energy harvesting system has two types of consumption. One type of energy consumption is a dynamic consumption, and it is due to activities. For instance, when the system transmits data. And another type of consumption is the static consumption. The static consumption comes from the sleeping, for instance, mode of a system. It's because of the leakage of the devices and components there. These two consumptions add up and they make the whole consumption of an energy harvesting system. Before talking about the design of the node, we need to take a look at the state machine of the system, which is very simple. The system is in sleep mode most of the time. It wakes up after a period of T when, for instance, the timer in an MCU overflows, and it goes to the transmission, sensing and transmission mode. So most of the time, the system is in sleep mode, and this makes the static consumption as we talk. And when it goes to the sense and transmit mode, it causes dynamic consumption. After sensing and transmitting this data, the node again goes back to the sleep mode, and it stays there for a longer period of time. And then this cycle repeats over time. When we design a LoRa node, we need to take into account different factors of consumption. The first one is the LoRa module itself. So it really depends on the settings that we or the designer chooses on the module. For instance, the bandwidth, the spreading factor, and the transmission power. And another reason for the LoRa module consumption is because of the different manufacturers. So different manufacturers, different component part numbers have different consumption. So the designer needs to keep in mind to go to the datasheet and compare the different modules and pick the one, in this case, which has the lowest energy consumption, because the system is very limited in terms of energy budget. Another source of consumption is the software algorithm. It really depends how your algorithm, how you develop your algorithm, how efficient it is. So it really depends how much we process, how many times per wake up we measure, and how many times we try to send the data or transmit the data. And the other thing about the algorithm is not only about sensing and transmitting data, but also need to be aware of hardware and using your software or algorithm to keep unnecessary blocks off. Because if you don't care about these parts, you will have sometimes some blocks on and this causes some consumption, but it's not necessary and it's a waste of energy. The next one is the circuitry around for instance, the LoRa module to make it work. It's about the sensor. It's about the sensor. So we use, for instance, temperature sensors or humidity sensors. They also consume something that it needs to be kept in mind. Another one is the low dropout regulator. Sometimes the voltage from storage or the rest of the blocks do not match. So we need to put an LDO to decrease the voltage. And also the storage is not an ideal element. This means that there is some leakage. So whatever we store in the storage, we waste some part of it in the storage. And this needs to be kept in mind as well. It was so far about the consumption, and we need to take a look on harvesting. A harvester have, in this case, it's a PV, have different parameters that we can take into account to absorb as much as possible. One of them is the size of harvester. So the bigger the harvester is, the more energy we can absorb. The next one is the placement of the node. For instance, it should be really exposed to the light to get the most of energy. Also, the exposure time to the light. So it's obvious the more time it is in front of the light, the more energy we can absorb. Here you see a graph that shows the power vs versus the light intensity, and then this is really helpful to find how much power we can get in a specific amount of light. For instance, in 20,000 lights, we can get around 26 milliwatts of power. But this is only power. We need to have the energy because this is the language we talk in energy harvesting. We need to know the energy. But before that, we need to also check the light intensity over time. For instance, in a typical day, from 2 p.m. to 3 p.m., we have around 45,000 lights. Using this graph and using the previous one, we can have the energy of the system. For instance, from 2 p.m. to 3 p.m., here you see the energy vs time, and we have around 190 joules, and gives us a good overview how much energy we have in 1 hour block of a day. So it was about the energy consumption and energy harvesting. Let's take a look very quickly on the blocks of an autonomous LoRa node. You will see there are 4 blocks here. We have the external MCU in case you want to use the external MCU out of the LoRa module in case there is no internal MCU. We have the power side here, which is the energy harvesting PMIC goes to this part. And we have the LoRa module, and at the end we have the sensor header, which we can plug different type of sensors. This is also the 3D of the design. You can see the Nowi PMIC here on this side, the LoRa module. We have the MCU here. We have the sensor header here. You can change it. You can plug different type of sensors here. And we have the PV headers here. So these are 2 headers on the bottom, on the top to connect PV cell. And you see the storage pins, the battery pins here to store the energy. And we have different pins for debugging and measurements in case we want to measure current or energy.
Hi everyone, I am Tibor Keller, application engineer at Nowi. I will briefly introduce you the basic hardware functions of Nowi autonomous LoRa node. This development tool contains 3 well-defined electrical parts. The first is the RF communication part. The second is the energy harvesting power supply based on Nowi's NH2 energy harvesting circuit. The third one is the sensor socket that enables a customer using several hundreds of pre-built sensor sensor boards. RF circuit is based on Murata's sub-gigahertz low-power RF module, which runs the user application and LoRaWAN stack on its internal microcontroller. The 50 ohm electrical load, probably an antenna, an external antenna, could be attached via this UFL connector. Energy harvesting power supply is based on Nowi NH2 harvesting integrated circuit, which directly converts the energy coming from an external PV cell through this header and charging the attached lithium or lithium polymer battery. Then the currents of every individual blocks can be measured via these pin headers. The last part is the sensor header, which enables powering and analog and digital interfacing the external sensor board, and then customer can use several hundreds of pre-built boards like what I'm showing, designed by Nowi.
Hello everyone, I'm Mert from Nowi. I'm responsible for the software development of our long-range wide area network project. Now I will briefly discuss the key facts of our software architecture. In this project, we are using TTN gateway, which is one of the basic gateways. It can be used for either indoor or outdoor applications. This is our hardware for this project. As it was mentioned, there's a Murata model, which is the RF LoRa model. Under that, there's an STM32 microcontroller. This is the sensor board. It has BME680 Bosch sensor for temperature and humidity sensing. We are doing solar energy harvesting in this project. The basic flow involves that the STM microcontroller gathers the data from the temperature sensor, and then it sends the calibrated data over the gateway, and then we can see the temperature data on TTN console, like in here. As you can see, 2 bytes of payload are being sent, and these are the hexadecimal values of the ASCII characters that are being sent. So 32 and 33 indicates that 23 degrees are sensed and are measured by our temperature sensor. For software development, we are using Kyle IDE, and we are also using the ST's already developed library, but of course the one should change and make configurations according to their applications. As you can see in the TTN console, for this application, just for debugging, we are sending data once in each 50 seconds. But of course, in the real-time application, it won't be like this. It will be around 1 day, maybe even more. So this application transmission duty cycle shows the data period, 50,000 milliseconds, but it will be way more, again, to mention. Now, the main flow of the program is, again, the MCU collects data from the sensor. They communicate with I2C, as you can see in here. And then after it sends the data in here, the Murata model and the MCU and the sensor enters low power deep sleep mode. From the low power deep sleep mode, they wake up with RTC alarm. The RTC alarm ends around after the duty cycle finish. So this transmission duty cycle also indicates the RTC alarm time in this project. The TTN application numbers are entered in the commissioning header of ST's library. So the globally unique identifier numbers, the network session keys, and each keys like that are entered on this header. Activation by personalization protocol is used in this application, so there is no overhand shaking. The device is ready to communicate on the network without any additional procedure, and the end device does not have a network key or application session key. They are configured at production time. These are the key facts of our software architecture in this project. Thank you for listening.